is not the title of my talk. It's just the quotation to go before the talk. And it's the last talk. So I'm going to take you back to week 1, I guess, apparently, when you talked about moisture. And it's not really, it's not something I do, so this project has been a little bit of a sort of a side project for me, a little bit of a hobby over the past few months or so, and joint work with John Thuburn at Exeter, Hilary Weller, who's at Reading, and Steve Tobias. Actually, there's two different talks I'm going to give, but as usual, I might not get to the second one. We'll see. But if you'll give me a bit of latitude in this talk, the subtitle is Inventing Equations for Convection. And so I don't know whether what I'm about to talk about here will have any impact or be any use whatsoever in the future. It might just die within a couple of months and not go anywhere. But since it's the last talk, what the heck. And as usual, interrupt with questions. And part of it was that I kind of started looking at moist convection, and it struck me that moist convection was going a little bit the way of GCMs. So if somebody runs a GCM, a big full GCM at NCAR, and they describe their results, and somebody wants to reproduce their results using another big GCM, some of them you can, but to really reproduce their results, you actually have to get the code from them and then run the code. You can't reproduce their results just by them telling you what they've done in a paper. And reproducibility is meant to be one of the primary cores of, of science, of experimental science. So it struck me that moist convection was going a little bit like that. Everyone has their own moist convection codes, and they're all a little bit different. They all have different microphysical schemes or whatever, and so they're all a little bit different, and people are getting different results. So in a way, I wanted to kind of bring it back a little bit to GFD. We always want to go back to GFDL. It's the home of it's the home of everything. But anyway, I don't really want to go back to. I'm quite happy at Exeter, by the way. Also part of it was I was invited to write this review article. I wasn't given the title, but the editor of the Proceedings of the Royal Society wrote to a few people and said, "Can you write a review article?" The editor was Steve Tobias in this case, and he said, "But I don't want you to write a review about what's happened in the past. I want you to write a review about the future." So it's always a bit hard to write a review about the future, but nonetheless, it was sort of where GFD sits into the whole panoply of atmospheric science, and I kind of talk about the atmosphere and the ocean are complex things, and of course we need complex models, and we do need full GCMs, as Isaac has mentioned. We don't want to avoid using them, but also there's kind of an approach. I think GFD has a certain style, which is that you try and reduce the problem. The GFD style is to try and reduce the problem to its bare minimum, but no further. You do want to capture the essence. So it was with that kind of thing that wanted to do look at moist convection, and all the hip people are now doing moist convection. So I wanted to join that party, but this has been a bit slow actually, because I've been doing some of my own coding, which is really slow when I do it, even today with sort of modern Python tools. And anyway, in today's talk, so this is sort of a seminar, but I'll try and be pedagogical as I go along. Talk about two things: a two-fluid model of convection and Rayleigh-Bénard convection with moisture. We'll see. I'd like to get to the second topic too. I don't have as much to say, so it won't take as long. So thinking of moist convection as a problem in GFD. We have convective parameterizations as has come up. And we have convective parameterizations. Why? Because climate models have a horizontal resolution of whatever it might be, say 50 kilometers for climate model. Convection has a horizontal scale. Well, it's not terribly well defined, but one might think of it as of order 1 to 10 kilometers, sort of a horizontal scale, perhaps similar to the vertical height of the atmosphere. The plumes themselves might be a lot narrower than that. So it's often actually perceived that GCMs will fall over or blow up or give nonsensical results without a convective parameterization. Resolution's too low to resolve convection, therefore they produce unrealistic grid point convection. Locally too strong, blah blah. Timing of convection is all wrong if you don't have this convection scheme. And then what you will end up with grid point convection. But a grid point should convect, or you might wish it to convect, even when the mean conditions are stable, because some parts of the cell will be unstable. So even if the mean is stable, you might wish for it to convect. So a convective parameterization scheme would hopefully do that. So it might convect even when the flow is stable. And of course the ideal one would solve all of these problems above. It's also perceived, or certainly a perceived problem, as to what happens when the model starts to resolve the convection. So if it sort of poorly resolves the convection, do you parameterize it or do you let the model do it? This is the so-called gray zone problem people talk about. The gray zone problem is when your model is starting to partially resolve it. And that problem is also perceived to arrive in oceanography in mesoscale eddies, that you partially resolve them. So convective parameterization schemes, sort of the main ones in current use. The first class of models really which were proposed were simple convective adjustment problems, or convective relaxation. You relax back to some profile. And in a sense, the whole notion is this so-called quasi-equilibrium, whereby the convection happens on a much faster time scale than the large scale flow is occurring. So if it's unstable, convection occurs, brings it back to some, say, a moist adiabatic profile on a fairly fast time scale. And so if the profile is unstable, in these schemes you adjust it or relax it to some marginal stability on some fairly fast time scale, and you try and conserve the things that you should conserve. You want to conserve some measures of energy. So convective adjustments got along, goes back to the 60s, perhaps even more. Then there were these mass flux schemes, which Arakawa and Schubert popularized, or in many ways invented, although there seemed to be some precedents in the literature before them. Klaus Friedrich. What they did was in a sense, partition the fluid into convecting and non-convecting fluids. So you said, okay, you've got a grid cell. Some of it's going to be convecting, some of it's not. The background is non-convecting. So then you apply various rules to the convecting fluid to neutralize the profile. And you flux, so they're called mass flux schemes. Flux, mass and buoyancy and moisture up into the upper atmosphere. Conserve the appropriate quantities, and you've partitioned the fluid into, say, convecting and non-convecting, and you treat them differently. You treat the background fluid with the dynamical core of your model, but you treat the convecting fluid with your convection scheme, which can be very complicated, especially when you want to conserve quantities. In fact, the UK Met Office has a mass flux scheme called the Gregory round-tree scheme. And it's 20,000 lines of code, and nobody can understand it because David Gregory is retired, and so it's complicated. And the third class, I don't really know where this name came from, and I don't like it, but it's what has become known as super parameterization schemes. I have no idea where this name comes from, or why it's even appropriate. But the idea is that you embed a cloud resolving model inside a coarse model. So at some particular grid points, you have a row which is much higher resolution, which is a cloud resolving model. So you embed it within the coarse model. So you surround the coarse grid point with a fine mesh. In practice, these have been done two-dimensionally, somehow assuming that the convection is a smaller scale. And it's enormously expensive, as you might imagine. It's not even... There's some success with it. It's not widely used. I can't imagine people choosing to use it. Yeah.
Yeah, I'm a bit confused by the idea. Why then, if in each cell you put a cloud resolving model, why don't you just do a cloud resolving model everywhere?
Yeah, that's a very good question. And well, because you're not actually surrounding. This is your coarse model. You're not actually filling in the entire thing. You might just have some cloud resolving model here, and another one here. So you are saving. There is a saving, but your question has indeed been asked by others. But there is some saving. There is some saving. And the problems, again, perceived problems that these are well, apart from super parameterization, which has its own set of features, these are column models. And they're not cast as PDEs, which you might think of or not as an aesthetic problem. So you're not actually solving the equations of motion directly for the convection. So that means the codes become complicated. Lots of decisions to make, and if statements. Lots of manual adjustments to ensure proper conservation, and complex codes, as I mentioned. And so on. So, and perhaps as a sort of a by the way, somewhat spookily, as there's a little bit of a pun here, GCMs do fairly well with no convection scheme. So this is work with Penny Mayers, a postdoc at Exeter. She was a student of Steve Sherwood, who many of you may know, and Mark Webb, who's a colleague at the Met Office. Spooky is a horrible acronym because it's both German and English. Selected Processes On-Off Klima is a German word for climate intercomparison experiment. They ran a GCM over, many GCMs over given sea surface temperatures with and without a convection parameterization scheme. And a dozen or so GCMs participated. And Penny chose 10 of these models. So you can ask, how well do these models work? So you just turn off the convective parameterization scheme. Just turn it off. That's all that they did. And here's the results. One of these is the full model. One of, with the convection scheme, one of them is actually observations from GCPC, a precipitation set, and one of them is the models without any convection scheme. And can you guess which one is which? Which is observations, which are the full models, which are the models with convection turned off? Any guesses? Yeah, go on. You guys, well, go on. Any other? Okay. Should we see? Okay. Da, 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 da. Is this your final answer? Or do you want to ask the audience? Okay. Here we are. So actually, you're both partially right. This is the observations, and this is convection off. This is AMIP, the full models, and that's the difference actually between conv off and AMIP. So it's so the two models to take home. Steve Sherwood, a colleague from Australia, is a big fan, if you will, of convection and clouds, and he thinks they're terribly important, which indeed they are. So he was looking for lots of differences here, but I was kind of most taken with the similarities, and there are some differences. Just one other point to make is that this is actually the models. Most models divide up the precipitation into a large-scale scheme and the convection scheme, and this is actually what the models do, the average of the models. So most of the models' precipitation is actually coming from the precipitation scheme. It's not as if that is a small contributor. When you turn off the convection, it's all coming from the large scale. So the large scale takes over. And there are differences, but I'll skip through them. So I guess modern GCMs do, in fact, a half-decent job on the general circulation without any convective parameterization schemes. There are differences in certain locations, but and individual models, it turns out, don't have the same responses to the convection scheme. Have I got? I can't. No, I didn't shut that. So the moral of the story, or I choose to believe that the morals of the story, is that the equations of motion themselves do a good job of simulating convection. So use them if you can. They know more than we know. So this led us. Yes.
Would you show us the distribution of precipitation for quick?
This?
Yeah.
Yeah, okay, this is the this is one thing where they are different. This is the histogram of the distribution of how percentage of grid points have a certain amount of precipitation more than a certain amount. So what you're getting is when you turn off convection, you're getting quite a lot of grid points having not much convection. So there indeed are differences in the distribution. And perhaps surprisingly, the GPCP and the AMIP, which is convection on, have a fairly similar distribution. So that's sort of good in a sense. We do need something.
Excuse me, like previous slide, the last sentence. So the equation of motion, are you referring to dry equations of motion?
No, these are actually the full equations of motion.
Okay.
These are, I mean, these are models with, these are full GCMs with moisture and an equation for moving around water vapor and condensing it. Yeah, so these models, this model, convection off, has no parameterized convection. It just has the equations of motion, the moist equations of motion, producing that precipitation.
Just a quick question. So I'm wondering if you have tuned the schemes, or I mean the model, when running the convection of simulation.
No, no, they weren't tuned. It was just turned off. So they were tuned, of course, with convection on, because these were the full models, and then the modelers were just asked to turn the convection off in the free atmosphere. So they do surprisingly well. And had you tuned them, they might have done even better, because you know, modelers will tune things together rather than separately. Okay, so so using the equation, it's a little bit, it's vaguely like what Isaac was mentioning in today's lecture, I think, of the hyperhydrostatic equations. You kind of modify the equations of motion slightly in this hyperhydrostatic rescaling. You enhance the vertical advection, but still you're using the equations of motion as much as you can. So what we're going to do here, and this is, as I say, I'll advocate for it in this seminar, but you know, I don't know whether I'm going to seriously advocate for it. We'll see. Is that we're going to divide the fluid into convecting and non-convecting components. You might have more. You might have an updraft, a downdraft background, and handle both components with the equations of motion. Somewhat inspired by models of chemical engineering. So we kind of have two phases, but it's not two phases like a gas and a liquid. These two fluids are existing side by side in the same grid point. So there's two fluids in the same location or in the same grid point. So we're trying to avoid a distinction between dynamics and physics, if you will. So you can imagine that if you have some, so if this is your physical space, and the different colors are, say, some different potential temperature or something like that, that in a given grid cell you will have a distribution of potential temperature. So you might have, if this might be a PDF in a particular grid cell. So in a conventional model, you'll just give one value to this to the velocity, to the buoyancy, to the moisture in a grid cell. We will make the radical step of giving two values to the moisture, or potential temperature, velocity, and so on, to in a crude way sample that PDF. And we would choose one of the values, as it were, to be, say, the background value, and one of the values to be the value of the convecting fluid, and then treat both of them with the equations of motion. So this is some, idealized PDF of some values.
But each grid cell, how do you get multiple values in a single grid cell?
Well, a single grid cell is 100 kilometers.
Yeah.
By 100 kilometers. Certainly, there is a distribution of water vapor and potential temperature within that grid cell.
Yeah, but you don't resolve that.
You don't resolve it. No, of course you don't resolve it, but you no, exactly, you don't resolve it, but nonetheless you can sample it by giving it two values, and then you have equations of motion for these two values. And it's a perfectly well-defined procedure, believe it or not. So let's, and I should say there's one or two precedents in the literature. There's a paper by Junichi Yano. I don't know if any of you know Junichi Yano. He's a very bright fellow, very hard to read his papers. And his approach seems to be somewhat different, especially in the pressure field. And there was a vaguely related scheme going back to Randall and Fowler, just to mention these. So, sort of instead of having physics and dynamics, we just have dynamics. That's the idea. So, so what are the equations? Let's just, to illustrate them, and you would do this for the moist equations, but to illustrate the idea, I'll do it with the dry Boussinesq equations. So no B for buoyancy, think of it as temperature, if you wish. Momentum equation, horizontal momentum equation. I use U for horizontal, V for the three-dimensional, just horizontal momentum equation, vertical momentum equation with the buoyancy term, the buoyancy itself, and mass conservation. So, I just write down the equations now, and I want to introduce a new word to the lexicon, by the way. This is use your imagination. So, so consider variables that are averaged over some large scale grid box. Suppose that fluid has two components within it, with fractional mass sigma 1, sigma 2. Sigma 1 plus sigma 2 equals 1, by definition. It's got two velocities, two buoyancies, one pressure field connecting them, which is a kind of a key aspect to it. And that's kind of like you think of what's often assumed when you think of bubble models of convection, plumes going up, and you do these partial arguments for stability. You assume that the pressure is the same in the buoyant bubble as in the background. So the total buoyancy is sigma 1 B1 plus sigma 2 B2. Total vertical velocity will be sigma 1 W1 plus sigma 2 W2, and so on for all of the variables except for pressure. And then we try and write down equations of motion for these. And as I say, they're existing at the same, in the same grid point. We're just sampling the distribution with two values. We could try and do it with more. Two is enough for now. So what are the equations of motion? As I said, I'll just write them down to begin with. These might be the equation of motion for mass conservation. Again, it's Boussinesq. d sigma 1 by d sigma 2 plus the divergence of sigma 1 v1 equals this term on the right hand side. Similar for sigma 2, the mass fraction of the second one, equals minus sigma 1, sigma 2. So these mass 1, 2 and mass terms on the right hand side would be actually the terms, these are your parameterizations. This is where you would actually have one type of mass being converted to another. It's your entrainment parameters in a conventional scheme and so on. If you add these two up, you just get, because sigma 1 plus sigma 2 is equal to 1, you recover the full mass conservation equation for Boussinesq fluid, that the divergence is equal to 0. Yes?
So in the first week, David Rumps gave a lecture about bulk plume equations. Is
Okay.
it the same, or?
I don't.
It looks like the same, but
Okay. Sorry, I don't.
I don't know. I was just asking.
I'd be surprised if it were the same, because I don't think this. But I honestly cannot say whether it was the same, because I don't quite know what he was referring to. So, but I don't. I suspect it isn't the same, because we haven't seen anything like this at all in the literature before. But maybe it is. I don't know. Then for the buoyancy, again, you would have two equations for buoyancy. This buoyancy 1 is advected by the first velocity. Buoyancy 2 is advected by the second velocity, with some buoyant exchanges between the two. B1 plus B12 and B21. And provided you choose, which you should choose these appropriately, when you add these equations together appropriately, these terms will cancel out, because all you're doing is converting buoyancy from one to the other. And so total buoyancy is conserved in the even with the relabeling. So this conversion, you can either regard it as you're relabeling one fluid to be the other fluid. Well, let's just skip to vertical momentum. Again, you have two equations for the vertical momentum. Separate equations. You can also have two equations for the horizontal momentum, although you can actually choose, if you wish, to have the same horizontal equation for both fluids, but you have different vertical equations. And it's perfectly legitimate to do that. And so that's just what you would write down. You can also actually derive these equations. I kind of think, when I see sets of equations, you want to be able to derive them, and you want to kind of guess them too. And it's the same with quasi-geostrophic equations. If you kind of have enough intuition, you can almost write down the quasi-geostrophic equations in a couple of lines. Say this term's small, this term's big. Wave my hands, and out come the equations. But you should be able to derive them in a slightly more rigorous way, and you can do that with the full equations of motion. It's kind of an extensive practice used in large eddy simulations, that you would take. We label each piece of fluid with a Lagrangian label equal to 0 or 1. So, and these are advected. Lagrangian label is conserved. And then you also have a filter, which is kind of what the large eddy people do. They apply some kind of filter, like a top hat filter or Gaussian filter, and thereby derive equations for the largest scales. And then all the other terms involving the smaller scales get put over on the right hand side, and they are your Reynolds stress terms. And it's how you derive equations for large eddy simulations. They have a filter, and you're just explicitly simulating the larger scales. So we do that, but plus we have these Lagrangian labels. So then if an over bar denotes the filter, sigma is the volume fraction of the ith fluid. The sum of the sigmas is equal to 1. We might think of that just being sigma 1 and a sigma 2. Then you could take the mass conservation plus a Lagrangian label, gives you this equation. Then you apply this filter, gives you this equation. And you end up with this then being the mass conservation equation. This is actually for the full equations. For the evolution of the density and the volume fraction of the ith fluid. So that's a derivation, if you will, of the evolution equation. And then you can go through this, and I won't go through it in detail, but the tracer equation satisfies, say, this equation. Eta might be potential temperature or something like that. You apply the Lagrangian labels and the filter. After a few lines of algebra, you actually get that the ith potential temperature, call it, is advected by the ith velocity, and plus you have some sub-grid scale terms on the right hand side, and same for momentum, and these sub-grid scale fields, I haven't written it down here, but there'll be two components to them. One will be the exchanges between the two fluids, and one might be some sub-grid scale diffusion term, which we might parameterize with a hyperdiffusion or a Smagorinsky viscosity or any which way. And as I say, we're choosing the filter scale pressure to be the same in all components. It's a similar assumption to that made in partial dynamics. So, and it really has to do with the fact that we think that if there is a pressure difference between the ascending plume and the background, that the time scale for some acoustic wave to propagate across a cloud and remove that unbalanced pressure would be very small. So we're assuming those fluctuations don't exist and it happens instantaneously. And that has some useful numerical properties too. So you should emphasize that what we've done by this scheme is just to partition the two fluids. In a sense, you might argue that we haven't solved the essence of the problem. I mean, that's still there, which might be how much, when a bubble rises, how much of the outside air is entrained into it, and what happens when it detrains at the top. Those will be parameterization terms which appear on the right-hand side. What you have done is actually you're going to explicitly use the equations of motion to solve how this bubble goes up. So yeah, so okay, relabeling or conversion terms. This is where the parameterizations enter. I say it's in the relabeling or conversion terms, and that will, this is where your convection knowledge will come in. That you have to partition the fluid in the boundary layer one way or another, but there's some nice properties of these. I'll come to in a minute. If you don't have any right-hand sides, and the two fluids initially have the same properties, they will keep the same properties. They'll act as one fluid. here are some kind of simple, perhaps a simple parameterization of what the mass exchange might be. It would just be some relaxation of the two fluids towards each other. A mass exchange proportional to the difference of the two masses divided by some time scale. A buoyancy exchange between the two of a similar nature, such that the total buoyancy is conserved, the total mass is conserved by construction. So I should say we haven't done any serious thinking about these. Our hope is that we can actually borrow expressions for these schemes from these complicated mass flux schemes where there's been years of experience designing these entrainment schemes and then put it into this scheme. So it's a little bit different from conventional mass flux schemes because using the equations of motion. Conventional mass flux schemes also normally assume only a tiny fraction is convecting. These equations also conserve things nicely, which I think is what you want. They conserve things automatically. If the right hand side is 0, sort of the adiabatic case, it turns out that these equations conserve potential vorticity, for example, with a slightly different definition of potential vorticity. Instead of just omega dot grad theta over rho, it's omega dot grad theta over sigma times rho for the potential vorticity of the ith fluid. Again, if you don't have any right hand sides, you can go through derivation and show that the total energy is conserved automatically by the equations. So you don't need to do anything, you don't need to build that in, so to speak. It's automatically conserved. And the final little property to show is that you can actually linearize these equations. For example, these just to find out what the normal modes of these equations are, and they behave in sensible ways that you actually get. You're going to actually get a couple of extra modes floating around because you have more time derivatives, but you end up, for example, with a standard combined inertial gravity mode. This is one of the dispersion relationships which comes out. Then you also get actually two fluid modes. These are the linear modes. So just if you divide a fluid up into two, solve our equations, just perturb it and see what waves come out. You'll get the standard waves, and you'll also get this two fluid mode when one fluid is going up and one fluid is going down. But it's all sort of sensible in a sense, and that's about as far as we've got. Want to just show you a couple of other little things. I tried to show this movie at a meeting about a month ago, and it just didn't play for some reason. Let's hope it does now. We'll see. Here's actually a numerical simulation. So these are actually the two-dimensional Boussinesq equations, dry in this case, as a demonstration. And I've taken the B1 and B2 are the buoyancies of the two fluids. So this is an initial value problem. So B1 is buoyant here, negatively buoyant here. B2, the other fluid, in the same location is buoyant here and negatively buoyant here. So the total buoyancy is like this, with nothing in the middle. And now we let it go. And what will happen, this is what we wanted to happen, is that this will of course go up, is buoyant. This guy will go down, and in the middle you've got two fluids occupying the same space. The buoyant one will go up and the negatively buoyant one will go down. So you'll actually have some convection going on even when the mean is stable. And if this works, we will see. So here are the initial conditions again. Okay, nothing in the middle, and let's just see what happens if it works. There we go. And that's about it. That's the extent of my no Oscars here. Let's do it again. Okay, it's buoyant here. This fluid is buoyant here, negatively buoyant here. This fluid is buoyant there, negatively buoyant there. So the total buoyancy here. So if you just want to watch one panel, watch this one. And what we've got here is the actual difference in the amounts of mass between the two. So everywhere in the initial conditions, half of it is fluid 1 and half of it is fluid 2. So keep your eye on these two. There. If I can stop it, I wonder. Guess not. Don't know how to do that. So it's behaving in a sensible way. Does the partitioning matter if both fluids have the same buoyancy? No, it doesn't. I'll skip that. Here's another little problem. Again, it's a toy problem. But we took actually, this is going to be a statistically steady state. We took so it's a Rayleigh-Bénard problem. Rayleigh-Bénard convection typically is buoyant at the bottom, negatively buoyant at the top, so plumes rise. So we did a problem here where the total buoyancy at the top and the bottom is 0. So in the mean, the fluid is not unstable. So you can imagine this entire box would be it's a grid point which is not unstable. But we partitioned the boundary conditions so that one of the fluids, in fact fluid B2, was actually unstable. Fluid 1 was stable, and combined together they were exactly stable. Okay, so if this were a one fluid model, it would be exactly stable. And so these are just the initial conditions. There's just these numbers are very small, but the total buoyancy here, you can't really tell from here, but it's the same total buoyancy at the top and the bottom. And we'll see if this works. So it's actually working. So what actually you're getting, in spite of the entirety of the fluid being stable, it's actually convecting, because you have one unstable fluid, a small proportion of one unstable fluid B2, which is punching through the background and giving you convection. And so you're getting this convecting flow. And that actually turns out to be, whether you get this convection, turns out to be rather sensitive to the parameterization of the mass exchange between the two. So what we did in the second is that we increased the exchange between the two and made it rather strong. So that as soon as a buoyant plume leaves, it's exchanging with its surroundings, and it's trying to become one fluid. And one fluid with these boundary conditions is not unstable. So when we did this, well, it's not quite as easy to see because this color, I haven't figured out. I'm not very good with color schemes, so it shows its own color scheme. But with a larger entrainment parameter, you're actually getting much weaker convection, and the way to tell that is to look at this number here, which is 0.06. So you're getting much weaker convection, whereas if I go back to the small entrainment, this number is about 0.2. So you have much, so I can kind of tune the amount of convection I want by tuning this entrainment parameter. If I set the exchange to 0 for this problem, yes, then this fluid would be unstable, but I won't have any entrainment. I haven't actually done that, but it's good. Why haven't I done that? It's an obvious thing to do. I don't know why I haven't done that. Okay. Not sure why I haven't done that. Okay, so that's kind of the end of this, I think. Let me skip this. This was an attempt. John. So in the Rayleigh-Bénard problem, how you choose, you have to sort of set the partitioning, and in the Rayleigh-Bénard problem it's set through the boundary conditions. So at the top and at the bottom, in the normal Rayleigh-Bénard problem you're just setting B at the bottom and at the top. So in my problem I'm setting B for each fluid at the bottom and at the top, B1 and B2 here at the top, and the mass fractions. So B2 at the top is negatively buoyant, minus 1.8, but it only has a mass fraction of 0.1. B1 has got this value, so that the total buoyancy is 0, and at the bottom I set it to be the opposite. B2 is plus 1.8, again with a small mass fraction. So the fluid with the small mass fraction is unstable, but the total fluid is not. So what happens is that because I partitioned it, this fluid with a small mass fraction can kind of punch through the background and convect all by itself. So in a real convection scheme, in a GCM, it's not Rayleigh-Bénard convection. You'd have to set this partitioning. You'd have to have a scheme for that in the boundary layer. Yeah.
So I have a naive question. I mean, here you put some diversity inside each cell for the initial condition by these two value of buoyancy, for instance. But isn't it the case that along the dynamics, this diversity will decay? I mean that the cell will become more and more uniform.
Oh yes, you have to. So you have to.
And if it's not the case, I mean,
if it's not the it won't be the case, because that will be the job of your boundary layer scheme, to create the diversity. So you will be having some boundary layer scheme, which will. So you've kind of shifted the problem for a boundary layer scheme to creating the diversity. So your boundary layer scheme now becomes responsible for deciding how much might be convective and how much would not be convective.
So for the actual dynamics, another way is through turbulent mixing, probably. I mean, this is.
Well.
I mean, around there. I mean.
Yes.
If you.
Yes, but what you're somehow will still have to do is you'll still have to partition it in the boundary layer. There'll be no avoiding that, I think, and but
I'm struggling with this a little bit. I'm trying to understand what the ground truth is here. Let's say I'm trying to compare this to the right answer for this problem.
Yeah.
So in this case with 0.1 for sigma 2, suppose I run a simulation with 10 times the resolution in the horizontal, and every 10th point, maybe randomly, I change the buoyancy in the boundary layer.
I think your ground truth.
Would that be the grand truth?
It would be something like that. That you would have, if you ran it with 10 times as much resolution, then you would have boundary conditions at the top, which were not uniform. You would have different values of B1 and B2. Yes, I haven't done that. Yeah, I haven't done that. That's right. But that would be the ground truth. So, right. So if I had a high resolution model, very high resolution model, so instead of these being uniform, because what you're kind of imagining is that you're not resolving the variations along the boundary. So you'd have, so in some places, you'd have unstable columns, and other places you'd have stable columns, and it would convect in some places and others. But yes, haven't done that. Yes.
Yeah, I had a bit of a similar question, but I'm puzzled by your answer, because there is no ground truth here. Shouldn't you specify for a ground truth to exist? Shouldn't you specify, for example, the viscosity, the thermal diffusivity?
Yes.
So that if you, if you do the problem at 10 or 100 times the resolution, you would have to specify those numbers.
You'd also have to specify. Yes. So I mean, here these have a particular Rayleigh number. So if you had much higher resolution, you'd probably want to reduce your viscosity and your diffusivity to have a higher Rayleigh number at the higher resolution.
So you're saying that you have viscosity and
yes, there's on the right hand side.
But what they're meaning then?
Well, they are eddy. I don't know whether I've written down. They are. I just have conventional viscosities and diffusivities on the right hand side, but in a sense, their meaning is that they are eddy viscosities for the large scale. So, in a sense, not only do you have an eddy viscosity, but you also have these exchange terms as well. And if you had a very high resolution model, you would be reducing your diffusivity and your viscosity also. So in a sense, I mean, the turbulence problem is harder when you have, say, moist convection. Because not only are you conventionally parameterizing entrainment into a bubble or something like that, but you might also have eddy viscosities and eddy diffusivities.
Coming back to the initial problem with clouds, compared to the Rayleigh-Bénard convection, I'm confused by the exchange term, because then if there is stratification, you may expect a different exchange term on the horizontal and on the vertical, or is it something exchange term between the two fluids? There will be more mixing on the...
Well, all I'm doing here, I mean, in fact, these are exactly the exchange terms which I'm using in that simulation. So I'm just exchanging mass and buoyancy. I'm not exchanging any velocities. So clearly got a long ways to go. But I think that's about. But let's a few more minutes. 2 minutes? Okay. How about 10 minutes, you said? End of part one. Okay, but I won't take very long about this. This is more of a, it's often said, and I think apparently somebody said this in your first week, Caroline, I think, that Rayleigh-Bénard convection is not a good analog for convection in the atmosphere, and you can think of 10 reasons why it isn't. But I'd like to make it one. I'd like to connect the two. It's a little bit like, I think, connecting, you know, a dry quasi-geostrophic model with a full GCM. You've got a ways to go, but let's at least try and make that connection with various things on the way. Let's try and make the bridge. It might require a few steps, but what we started with was actually start with Rayleigh-Bénard convection, and then you add condensation to it, and of course you've heard this joke now before. What you end up is Rayleigh-Bénard convection, and I'd like to kind of propose this as a little, perhaps the simplest possible model of moist convection. And one reason is, as I said, there are hundreds of papers on moist convection in the atmospheric science literature, but that number pales into comparison, pales away by the number of papers on dry Rayleigh-Bénard convection in the engineering and physics literature. There's actually very few papers on moist Rayleigh-Bénard convection. There's Olivier Paul Weirs has written one, and there are a few others. So it's Boussinesq fluid with two plates of different temperatures and a condensing component that releases Layton's heat, and it bridges this gap, because in a way there's a lot of fundamental questions in convection which you would like to address. You know, what are the controlling non-dimensional numbers? We don't tend to think about those problems for moist convection. You don't hear, if you go to a talk on moist convection in the atmosphere, you actually never hear anybody talk about the Rayleigh number. The Rayleigh number is probably pretty big, so you know, it's like 10 to the 30th. And I asked somebody in moist convection, why don't you talk about the Rayleigh number? He said, well, it's so big, it's infinite. But the thing about Rayleigh-Bénard convection, you know, conventional Rayleigh-Bénard convection, is that there is no limit of infinite Rayleigh number. The actual heat flux always keeps on increasing with Rayleigh number. So if you go from 10 to the 30th to 10 to the 50th, the heat flux will increase. And 10 to the 500th, it will increase more. There isn't a limit, it seems. So why isn't there a limit? And is there one for moist convection? So what are the, you know, does molecular viscosity matter? Is there an ultimate regime? This ultimate regime is what the physicists call this regime when molecular viscosity doesn't matter, but it always does seem to matter. What determines the heat and buoyancy fluxes, how far apart are the ascending plumes, and so on. And the thing about the equations of motion, here are the moist Rayleigh-Bénard equations, and that you can write them down and there is no ambiguity, and you can give these equations to somebody else and say these are the parameters, and they can solve them and get exactly the same results as you can. So it's a clearly well-defined, well-posed problem that's reproducible, and once you have a condensate, then you can start to relate it to the real atmosphere, and you can start to make it less like Rayleigh-Bénard and more like the atmosphere. So instead of Boussinesq, you can make it anelastic, and there's a lot of equations for a lot of large eddy simulations are anelastic. You could take away the upper boundary and make it, put a simple radiation scheme in. So you can actually go step by step from dry Rayleigh-Bénard to moist Rayleigh-Bénard to the full equations in a systematic series of steps, and at each step you have a well-defined system which people can study. So it's a hierarchy, I suppose, in that sense. And the only thing, what you've done here is you add a condensate, dq by dt. This is your condensate. When Q is bigger than a saturated value, it actually condenses quickly. This tau is small, so all the rain falls out in the simplest case, and then that condensation feeds back into the buoyancy. And then you have a bunch of well-defined non-dimensional parameters. You know, these are the usual suspects in the regular problem. The aspect ratio, the Prandtl number, the Rayleigh number are the only numbers that you have in dry Rayleigh-Bénard convection. System is perfectly defined by these, and there is nothing else. Then when you add moisture, there are some new non-dimensional parameters. There's a moist Rayleigh number, which kind of depends upon the latent heat of condensation. It's also well defined, and it might be quite large. And then there's a couple of non-dimensional numbers which emerge from the Clausius-Clapeyron relation, because we've assumed that the moist saturation is related exponentially to the temperature, which is so this is a well-defined system. You can actually, here's one of the non-dimensional equations. You can actually find an analytic solution to these equations, and this is actually a what I call the drizzle solution. When there's no motion, the ground is saturated. It's just diffusing in to the atmosphere. It's just diffusing in. It's condensing and raining out again. The condensation is determining its own temperature, is determining the temperature, and therefore when it saturates. And you can actually, you get a little nonlinear equation that you can solve for the drizzle solution. And you can solve that analytically, or almost analytically. And it drizzles. This is the actual sort of semi-analytic solution. The buoyancy increasing, the amount of moisture falls off almost exponentially. The entire atmosphere
can you
is
explain
saturated.
what drizzle means for non-English people?
Okay, drizzle is drizzle is a very common word in England. Drizzle means a very low level of rain. So in this model, the drizzle solution is that we have diffusion in from the ground. This is diffusion. This is providing moisture, and here it is raining out when it's saturated. This is the condensation term. This condensation then feeds back into the buoyancy equation. So you have again a sort of a diffusion condensation term in the buoyancy equation, and the saturation, the level of saturation is determined by the value of the buoyancy itself. So you can add these two equations together, and you get this conservation property, which you can then solve, and this gives you the actual solution. So it's just drizzling in, and but that's going to be unstable for large Rayleigh numbers. You can actually get all sorts of interesting behavior when you integrate them, and with increasing Rayleigh number, you can actually explore the behavior, and this hopefully will be a movie. There we go. All of a sudden, bang, and this is moist Rayleigh-Bénard. So in this particular simulation, which is 2D, you end up with a fairly steady solution of 3 plumes. If you increase the Rayleigh number more, you get more plumes and it becomes turbulent. But Antoine has stood up. This won't, because the Rayleigh, I don't think this one will, because I don't think the Rayleigh number is high enough on this. No, I don't have a movie. No, I think. Sorry, this has just stopped. So anyway, so I'd like to kind of encourage more people to think about this as a sort of a. It's a very rich problem that's simply posed. So anyway, there you go. Time for drink.
Thank you. Are there lab experiments of Renyi-Bénard convections? I mean, except England.
Of Renyi-Bénard? I don't know of any. It'd be great. I don't know how you would do a lab experiment of with a condensing fluid, but yeah, I don't know. So not that I know of, but if you know of any, let me know.
Could you explain why, by just adding moisture, Rayleigh-Bénard becomes appropriate?
Well, I'm not saying it becomes appropriate. I'm saying it's a step towards realism. Yes, it's not. All of a sudden, it doesn't become a model for convection for moist convection in the atmosphere. But it's one step towards it. It's and then I can, as you know, with two more steps, I can make it pretty much the same as a cloud, as a large eddy model with some simple parameterizations for convection. I can take the top boundary away and make it sort of radiatively cooled at the top, and I can make it anelastic. And then that's pretty close to what a lot of people use for large eddy models to actually study real convection. I've got a simple condensation scheme here. You could probably then additionally add an equation for liquid water and not have this, but I think there's a sequence of steps which will get you there. Isaac?
I think when people try to think about direct numerical simulation of radiative to convective equilibrium, it seems to be what you're aiming at. The problem that prevents you from doing it is that you'll never get into a regime, practically speaking, in which your vertical diffusion of buoyancy is negligible compared to your radiative cooling. That's the hard part. To be atmospheric, you have to have the radiative cooling dominant, and that's just extraordinarily difficult to get into that. And as long as your vertical diffusion of buoyancy is the dominant thing, that's not going to be atmospheric.
No, but that's a matter of getting the Rayleigh number high enough, I suppose.
Yeah, but it's just extremely hard.
Yes, it's extremely.
People say, "Oh, let's just do direct numerical simulation of radiative to convective equilibrium."
Oh, yes,
which is what you're aiming at.
That's what you're aiming at. Yes, okay. But I'd be happy to get halfway there. Yes, I'd be happy to to get. Otherwise, otherwise we've kind of given up before we start, and you can't imagine that it is the cloud resolving models are pretty complicated. So anyway, go on. Question over there.
The first thing that comes to mind about cloud convection is Rayleigh-Bénard convection.
Yeah.
So, like, why haven't people worked on this before?
I think they probably because of they think it's probably because they think it's unrealistic. Partly perhaps for the reasons that Isaac said. In Rayleigh-Bénard convection itself is a convection between two plates, which isn't terribly realistic. But I don't know why people haven't worked on it before, and but I don't think we can't always ask that question. you know, I don't know why people haven't done it before. It's you know, go on.
I was just going to ask. I've read briefly that Pauly-Schumacher paper.
Yeah.
I was wondering what the connection, because they didn't. Your equations aren't the same.
No, they're not quite the same. They have a different equation of state, which I couldn't quite understand where their equation of state was motivated by. I mean, our equation of state, which comes into the Clausius-Clapeyron equation here, is that the saturation vapor pressure is an exponential function of the temperature, and then the temperature is actually a linear function of the buoyancy, because the buoyancy here is akin to potential temperature. So that's what's advected around potential. Think of the buoyancy as potential temperature. The condensation depends upon the actual temperature, not the potential temperature. So you need a relationship between those. That brings in your other non-dimensional parameter. So
what's tau?
Tau is very small. Tau is the time it takes to condense once it becomes saturated. And in the so-called fast condensation limit, you make that as small as you can. So in the actual numerical code, you make tau to be a time step or 2 time steps. So it's essentially the condensation is occurring instantaneously. And in a code, actually, you don't even need to do it like this. You can just remove all the moisture. But you know, in the end, I mean, even forgetting about its relationship to the atmosphere, if you regard that as beyond our ken, so to speak, one thing about this system is that you do actually know what the non-dimensional parameters are. So you can actually say, okay, my Rayleigh number is this, my moist Rayleigh number is this, my non-dimensional Clausius-Clapeyron parameter is this, and this is what behavior I get. And as I increase these parameters or change these parameters, I'll get this and this bifurcation, and it becomes turbulent at these values. And you might not be able to get into this, the actual regime of what we had this afternoon of real rain, but at least we'll have some foundation.
There is a last question.
Yeah.
I was wondering, can you come back to your drizzle solution?
Yeah. Yeah, here we are.
Is that, I was wondering, is that your solution of maximal symmetry, like the one with constant temperature gradient you get for dry Rayleigh-Bénard? What happens if you assume a constant background temperature gradient?
Yeah, I'm not sure. So I'll go through the solution. So these are my equations. I'm diffusing moisture up from the boundary, and then it's condensing. Condensing is affecting the buoyancy, which is also diffusing up with the same kappa. I add the two together, and I get this conserved quantity. So this value b plus gamma q then will be a linear function. Then I say, and I can justify it asymptotically, that the actual value of q will be the saturation value of q, because it's diffusing up, becoming saturated, and then falling out. So this q is the saturated value of q. So b plus gamma qs is, if it's a second derivative, it's just a linear function, az plus b. And the a and the b are determined then by the boundary conditions which you impose. So b plus gamma qs is a linear function, but qs itself is a function of B. Qs is this exponential function of the temperature. So you get this equation, which is a nonlinear equation, B equals gamma exponential of B. So that's the equation you have to solve. So I don't know what its relation is, but it's the simplest background state, I think, in this problem.
Thank you, Geoff. Thanks a lot.